Here we are going to discuss about periodic motions and oscillatory motion. Those motion which repeats itself at some regular interval of time are called periodic motions. As for example, the motion of a rocking chair, motion of hands of a clock, motion of earth around the sun, these are all kind of motion which repeats themselves at some regular interval of time and are called periodic motions. A special type of periodic motions are oscillatory or harmonic motions, where the body moves back and forth, that is a to and fro motion through a particular path repeatedly about a mean position. So in this type of motion they are periodic in nature, as they are also repeating in regular time interval. The body moves back and forth through a particular path repeatedly about a mean position. Suppose the example of simple harmonic type motion is the motion of a bob of a simple pendulum, the motion of a loaded spring. These are some examples of harmonic or oscillatory motion, and by comparing these two definitions we may infer that all kinds of oscillatory or harmonic motions are periodic in nature, as they are repeating themselves over some regular interval of time. But all periodic motions are not necessarily oscillatory in nature, because all periodic motions are not to and fro in nature. So these motions are not oscillatory in nature. So all oscillatory motions are always periodic in nature, but all periodic motions are not necessarily oscillatory in nature. Here we have given the definition of a motion which is called simple harmonic motion or SHM. These are motions where a body moves back and forth about an equilibrium position such that a restoring force acts over the body. The restoring force which acts over the body is always directed towards the equilibrium or mean position of motion, and it is proportional to the displacement of the body from the mean position. As it is given here in this definition, if the force is proportional to the displacement and it is oppositely directed, so that it is always opposing the motion. So F is proportional to minus x, and if we write it as F equal to minus kx, where k is called the force constant, that is restoring force per unit length, and it is defined as force constant, and the unit SI unit is Newton per meter. So F is equal to minus kx we have, and also from the second law of Newton we know that force is equal to mass into acceleration, that is m into second order derivative of displacement d2x dt2. So from these two expression, F equal to minus kx and F equal to m d2x dt2, we can combine and we can write it as m d2x dt2 as equal to minus kx. Again d2x dt2 equal to minus k by m into x. So if we write omega as root over of k by m, that is the circular frequency or angular frequency of motion, we have d2x dt2 plus omega square x equal to 0. This is the differential equation of simple harmonic motion. This is a second order linear differential equation. And so from the definition we can infer the following, that restoring force is always acting over a body which is under simple harmonic motion. This restoring force is proportional to the displacement. The restoring force is directed opposite to the displacement of the body, and these simple harmonic motions must be periodic in nature, and the equation of motion can be represented by a sinusoidal harmonic sine or cosine function. Some examples of simple harmonic motions are motion of a bob of a simple pendulum. It is a motion of a bob of a simple pendulum is simple harmonic in nature. Motion of a loaded spring, oscillation of a magnet in uniform magnetic field. These are all examples of simple harmonic motion. Now here we are discussing about the relation between simple harmonic motion and uniform circular motion. As in this figure, it is shown that a body is executing uniform circular motion about a circle of radius, we may call it OA, with an angular velocity omega in anti-clockwise direction, and the value of the radius of this circle is A. It is OA, OB, these are the radius, it is A, and we are going to find out the relation between simple harmonic motion and this uniform circular motion. First of all, the body is in a direction, anti-clockwise direction, and it is rotating over the circular path A, C, B, D, again A. Now let us suppose the body at a particular point F over the circle, and it is making an angle omega t plus phi with OA. Now we are going to draw a normal from the point F over the diameter AB. So we have the normal drawn FM, where M is the foot point of the normal over the diameter AB, and we may call that the point M is the projection of the particle at point F over the diameter AB. As a particle moves over the circle from A to C, then C to B, from B to D, then D to A, and completes one complete rotation. Now while the particle moves from A to C, the foot point M moves from A to O. When the particle then moves along over the circle C to B, again the foot point of the perpendicular drawn from the point F, it moves from O to B. Similarly, when the particle moves from B to D over the circle, the foot point moves from B to O, and at the last quarter, when the particle moves from D to A and completes the complete rotation, then again it comes to A. The foot point comes to A, and it is from here we can see that a complete rotational motion by the particle is equivalent to the motion of this foot point of the normal drawn from the position of the particle over the diameter of the body is to and fro. Thus we can see that during the motion of the particle uniformly over the circle, the point M moves to and fro about the equilibrium position O. Thus from this discussion we may infer that the simple harmonic motion can be compared to the projection of uniform circular motion over a diameter of a circle. Now from here this circle is called the circle of reference, and the triangle OFM, from that triangle we have cos omega t plus phi is equal to OM by OF. Here OM is x at a particular point, it is x defined as the displacement from O. The OF is the nothing but the radius of the circle, it is A. Then from here we have x equal to A cos omega t plus phi, where A is called the amplitude, omega is the angular frequency, and phi is the initial phase. So thus from this slide we can relate the simple harmonic motion with uniform circular motion. Some important quantities related to oscillation. As here some definitions are given. What is called oscillation? Oscillation is nothing but one complete to and fro motion starting from a particular point and ending also in that particular point. If we start from, suppose in this figure we start from B, a body moves along the path BOA, then again returns from A through the path AOB at the point B. This is a to and fro motion, and it is starting and ending from the particular point B. So this is called a complete oscillation. This can be considered as a complete oscillation. And what is called time period? Time period is nothing but the time required for a complete oscillation. It is a time, it has the unit of time, it is second. And the frequency is nothing but the number of complete oscillation performed by the body per unit time. Its unit is hertz, and it is related to the time period as if it is inversely related to the time period, it is equal to 1 by time period. And the relation between the angular frequency omega and the frequency is omega is equal to twice pi. And its unit of frequency is hertz, and where the unit of angular frequency is radian per second. And what is called the amplitude? That is the maximum displacement of the vibrating or the oscillating body from its equilibrium position is called the amplitude of motion. In the figure we can see from the equilibrium position is O, and in both sides A and B are the maximum point of or displacement, that is the terminal points, and they are defined as the amplitudes. Its unit is meter. And what is phase? Phase gives the information regarding the state of motion. Both position and direction information can be obtained from the expression of phase. If we have x equal to a cos omega t plus phi, the total term inside the bracket omega t plus phi, that is the argument of the cosine function, it is called the phase. And here phi is called the initial phase. Hello dear students, as you know, the differential equation of a simple harmonic oscillator is a second order differential equation, and our task is to solve this differential equation. And in this lecture we shall see how we can solve the differential equation of a body executing simple harmonic motion. So as we know, this is the differential equation of a body executing simple harmonic motion, that is d2x dt2 plus omega square x. This is equal to 0, where omega is the circular frequency. Now if we call it equation number 1, and we are going to solve this differential equation through the following method. Now if we multiply both sides of this differential equation with 2 dx dt, multiplying both sides of this differential equation with 2 dx dt, we have now from equation 1 we can write that 2 dx dt into d2x dt2 plus omega square x into 2 dx dt. This is equal to 0. This is equal to 0. Now our task is to rearrange this equation. We want to just rearrange these two terms by, as it can be written as d dt of dx dt whole square. Look here, it is 2 dx dt, then d2x dt2 plus omega square is a constant, so we can write it as ddt of x square. This is equal to 0. Look here, it is 2x dx dt. Now by combining these two equations, we are just combining these two equations. How we can write it now? It is ddt as dx dt whole square plus omega square x square. It is equal to 0. Just combining these two terms in a single term. And look here, the first order derivative of this term vanishes, and if we integrate both sides, now we know that if the first order derivative of something vanishes, it should be a constant. Integrating in both sides, we have from this equation, that is dx dt whole square plus omega square x square. This is a constant. And now, and if this is a constant, from the boundary condition we can determine the value of this integration constant. And what is our boundary condition? As we know from our earlier knowledge that if we have a body executing simple harmonic motion, its velocity is 0 at its maximum displacement from the equilibrium position. Suppose we consider the motion of a body of a simple harmonic oscillator. Suppose we have a simple pendulum, and if we take it at one of its amplitude of displacement, suppose it is moving along this direction, this is A, it is the amplitude, then at this position the velocity becomes 0. At where? At x equal to A, at its maximum displacement. Its velocity becomes 0. Now putting in this boundary condition, putting in this equation number 2, we have our boundary condition. It is dx dt equal to 0 at x equal to A. That is at the maximum of amplitude. So here if we put it, we have C equal to, putting all these in equation number 2, we have, putting all this in this equation, we obtain C is equal to omega square A square. So the value of the constant is determined. So from equation 2 we have dx dt whole square plus omega square x square. C is omega square A square. So we have dx dt, this is equal to, we are taking only the positive root here, and we have positive sign, we are just taking, we have dx dt is equal to omega into root over of a square minus x square. Now if we mark it as equation number 3, it can be easily be integrated. Look here, it is dx dt omega into root over of a square minus x square. Now we integrating we have dx by root over of a square minus x square, this is equal to omega dt. What is this value of this integration? It is nothing but sine inverse of x by a, this is equal to omega t plus some constant of integration delta. It is a constant of integration. So we have from here, it is x by a equal to sine omega t plus delta. So we have x equal to a sine omega t plus delta, x equal to sine omega t plus delta. So this is the solution for the differential equation of a body executing simple harmonic motion. Now what is A? Here A is known as the amplitude of the motion, omega is the circular frequency of the motion, the total term inside the bracket is called the phase, and delta is called the initial phase of the motion. So this is the solution equation 1. So today in this lecture we have just solved the differential equation of a body executing simple harmonic motion. So thank you. Hello. As we know, the differential equation of a body executing simple harmonic motion is given by d2x dt2 plus omega square x, this is equal to 0. Now this is a second order differential equation. It is a second order differential equation, and we have to solve this differential equation by adapting some specific techniques. Now suppose that x equal to e to the power pt is a solution of this equation. Suppose this is a solution of this differential equation. Now if it is a solution, now we have dx dt equal to, it is p e to the power pt, and d2x dt2, it is p square e to the power pt. So now putting all these in the equation number 1, we have, it is d2x dt2, so we have p square e to the power pt plus, just we are putting here, p square e to the power pt plus omega square e to the power pt, this is equal to 0. Now if we take common from here, p square plus omega square e to the power pt, this is equal to 0. And as we have taken e to the power pt as our trial solution, so we have e to the power pt is not equal to 0. This should not be 0. So we have from here p square plus omega square, this is equal to 0, and we have p is equal to plus minus I omega. As you know, what is I? I is root over of minus 1. So now putting all this value here, if we put what kind of solution, we have a x to the power ipt. So x is a e to the power I omega t plus b to the power minus I omega t, as there are two roots, one is plus I omega, another one is minus I omega. So we are putting all these in here, we obtain, this is a solution, general solution of this equation. And as we know from our knowledge of complex number, that e to the power I omega t can be written as cos omega t plus I sin omega t, and e to the power minus I omega t can be written as cos omega t minus I sin omega t. So if we put all these here and take common, we have a cos omega t plus I sin omega t plus b cos omega t minus I sin omega t. Now if we take common from here, and sine and cosine terms, if we take common, then what we have, it is a plus b cos omega t and I into a minus b sin omega t. And if we simplify again, if we write it as, this is a constant and this is also a constant, we can write it as x equal to a prime sin omega t plus b prime cos omega t. So this is our solution. Now we can rearrange this solution in a particular way so that we can directly write it in the form of simple harmonic motion. So now how can we write it here? If we have, now we have here x is, we have x equal to a prime sin omega t plus b prime cos omega t. Suppose this is number 3. Suppose this is number 3 and take a prime equal to some a cos delta and b prime as a sin delta. Then by dividing this equation by this equation, we have tan delta equal to b prime by a prime, and if we want to find out a, just squaring and adding, we have a is equal to root over of a prime square plus b prime square. So putting all this value in equation number 3, we have x equal to a sin omega t cos delta plus a cos omega t sin delta. So if we take common a from these two terms, we have sin a cos b plus cos a sin b. So you can write it as x equal to a sin omega t plus delta. Look here, this is in the form of simple harmonic motion. So the solution of the differential equation obtained here. Now we may have some special cases. If we have case 1, if we call it, if we have in this equation number 3, if we have a prime equal to 0 and b prime equal to, suppose it is a. Okay, suppose this is the equilibrium position, this is one of the maximums, it is a. Now a prime is 0 and b prime is a. Then from the relation here we have tan delta equal to b prime, it is a by 0, that is delta is coming out as pi by 2. Delta is pi by 2. So we have x equal to a sin omega t plus pi by 2. So we can write it as cos omega t. So from here we can see that at t equal to 0, x is equal to a. So this means that the particle start its motion from one of its maximum position, that is x equal to a. It starts its motion. And the case 2 is similarly, we can write it, if a prime is equal to a and b prime equal to 0, from the relation here we have tan delta equal to 0, that means delta equal to 0. So we have x equal to a sin omega t. Look here, at t equal to 0, x is equal to a. So x is equal to 0. So what is the significance of this expression? That at time t equal to 0, it starts its motion from the equilibrium position, from the mean position. the particle starts its motion. So this is the solution of a body executing simple harmonic motion. Let us suppose a body executing simple harmonic motion along the line AOB, where O is the equilibrium position of the body and A and B are the two extremum position, that is the amplitude of motion of the body, which is given by A. Now, as we know from our knowledge of the solution of a body executing simple harmonic motion, the equation of motion is given by x equal to A sine omega t plus delta. And if we take the initial phase as 0, then we can write, if the initial phase 0, we can write it as x equal to A sine omega t. At t equal to 0, x is equal to 0. That means at time t equal to 0, the body starts its motion from the equilibrium position. Then it goes to B point B, then comes back to A, then again at A, then come back to O, then completes its motion. Similarly, if the body starts its motion from one of its maxima, we can take x equal to A cos omega t. Look here, if t equal to 0, then here x equal to A. That is, the body starts its motion from one of its maximum points. So now the displacement can be written as A, both sine and cosine function, sine omega t plus delta. Look here, A is the amplitude, omega t plus delta, the total term in this bracket gives the phase, total phase, and delta is the initial phase, where omega is the angular frequency. So this is the displacement of a body executing simple harmonic motion. Now, if we want to find out the velocity, then what is the expression of velocity? We already know that velocity of a body is given by v is equal to dx dt. So now we have x equal to A sine omega t plus delta. So dx dt, that is the velocity, will be A omega cos omega t plus delta. Again we are writing it as A omega root over of 1 minus sine square omega t plus delta. We can write it as root over of 1 minus sine square omega t plus delta. Now, and if we a plus minus sign is there, and if we from here replace it, where what is sine omega t plus delta, this is x by a. So by putting it plus minus a omega root over of 1 minus x square by a square. So we have velocity equal to a cancels out, plus minus omega into root over of a square minus x square. This is the expression of velocity of a body executing simple harmonic motion. And now, if we want to find out where the velocity is maximum and where it is minimum, then look here, we can write at the equilibrium position, that is at x equal to 0, we have v equal to plus minus a omega, that is the maximum velocity. So we have the maximum velocity at the equilibrium position of the motion, and at x equal to plus minus a, that is at the maximum of the amplitude. It is, suppose it is O, it is plus a, it is minus a, it is going at the amplitude position, that is at the maxima position. We have, if we put it here, x equal to plus minus a, we have V equal to 0. So V equal to minimum. So V is maximum at the equilibrium position, at the mean position, and it is minimum at the maximum. So this is the expression of for the velocity, and the expression for acceleration. Again we have velocity equal to, just from here, a omega cos omega t plus delta. So acceleration is dv dt, that is minus a omega square sin omega t plus delta. Again look here, from here we have x equal to a sin omega t plus delta. So acceleration is equal to omega square x. So this is the expression of acceleration of a body executing simple harmonic motion. Now look here, from this expression, at x equal to 0, a is 0, and at x equal to a, the acceleration is, so again that is the opposite case of velocity, where it at x equal to 0, at the equilibrium, the acceleration is 0, and at the maxima of motion, that becomes, at the terminal points, the acceleration becomes maximum. So this is the minimum of acceleration, this gives the maximum of acceleration. So these are the expression of acceleration, velocity and displacement of a body executing simple harmonic motion. Furthermore, we again require an expression of the relation between the circular frequency and the time period. The time period is given by t equal to 2 pi divided by omega, because the time period is the time required for a complete oscillation. Through a complete oscillation, the total angular displacement is given by 2 pi. If we starting from a point, again come back to that point, then and the total angular velocity is omega, then time period is given by 2 pi by omega, the time required for a complete oscillation. And this is related to the frequency as 1 by t. So these are the expression for a body executing simple harmonic motion. Here we are going to discuss the graphical representation of simple harmonic motion. And suppose here AB, took here AB representing the line along which a body executing a to and fro motion about the equilibrium position O. It is a simple harmonic motion. The maximum of displacement from the equilibrium position, that is O here, are A and B in the both sides, and here the displacement is represented by maximum displacement, that is called the amplitude, is A. That is, we can say that Ax equal to A cos omega t, and we are assuming that the particle is starting its motion from one of its maxima, that is either A or B, and it is A. The length of this distance, that is the amplitude, is A, x equal to A cos omega t, as it is starting its motion from one of its maxima or amplitude or the terminal point. So at t equal to 0, x equal to A, that is at t equal to 0 cos 0 is 1, that is x equal to A. So x equal to A cos omega t is taken as a equation for the simple harmonic motion. And we know that omega, the circular frequency, is related to the time period, that is the time required for a complete oscillation or a complete rotation is given by omega is 2 pi by t, that is the relationship. The first of all, the displacement x is given by A cos omega t, and if we plot x along the y-axis, here in the graph 1, if we are plotting x along the y-axis and time along the x-axis, and here the maximum displacement at x equal to plus minus A, that is, if we plot the graph here, t equal to 0, at time t equal to 0, here from the equation x equal to a cos omega t, we have x equal to a. At time t equal to t by 4, that is when the particle is just at the position O, it is crossing, that is at t by 4, that x becomes 0. Then again at x equal to t by 2, it is at the maximum displacement from the equilibrium at the opposite side, that is equal to minus a, and then at 3t by 4 it is again 0, and at t it is a again. So if we plot it in a graph, what we can see here, if we plot it in a graph, that at x equal to a at time t equal to 0, so at t equal to 0 x is equal to a. As time increases, at t by 4 it is crossing the equilibrium position, that is again x becomes 0. So at time t by 4 it is x equal to 0. Then again at time t by 2 it is becoming minus a. Look here, at time t by 2 it is minus a. Again at time 3t by 4 it is 0. So thus at t it again becomes a and completes one complete oscillation. Then the motion continues. So x equal to a cos omega t is given by this graph. We can represent it graphically. And then if x equal to a cos omega t, then what will be the velocity? What will be the graph? What will be the nature of velocity? As it is also expressed by a sinusoidal function, it is cosine omega t. So for velocity, we know that x is a cos omega t. So v is first order derivative, that is the dx dt, is a omega, that is a minus sign, sine omega t. And if we reorganize it, we have a omega cos omega t plus pi by 2. So now here if we plot it in the graph, at time t equal to 0, t by 4, t by 2, 3t by 4 and t, we obtain from v that at time t equal to 0, v is 0. At time t equal to t by 4, that is omega into t by 4, omega into t by 4 means that is from here pi by 2, that sine pi by 2 is 1, so we have minus a omega. Then at t by 2, we have sine pi, that is 0. At 3t by 4 we have 3 pi by 2, that is becoming sine 3 pi by 2, that is plus a omega. And again at omega t at 2 pi, this is again 0. Now if we plot it in a graph, we obtain this graph. At t equal to 0, t by 4, t by 2, 3t by 4, t, we are plotting all the point, we get again a sinusoidal graph is obtained. But here look here that there is pi by 2 phase difference between the displacement and the velocity of a body executing simple harmonic motion. And now similarly, if we plot the acceleration, we know x is a cos omega t, so dx dt is minus a omega sine omega t, d2x dt2 is the acceleration, it is represented by small a, it is minus a omega square cos omega t. So from here it is, if we rewrite it, a omega square cos pi plus omega t. So look here, pi phase difference between the acceleration and the displacement. Acceleration and displacement expression, there is pi phase difference. So if we put it at time t equal to 0, t by 4, t by 2, 3t by 4 and t, we are just obtained from this equation, that is at t equal to 0, acceleration becomes cos omega t, that t equal to 0 minus a omega square. At t by 4 it is 0, at t by 2 it is plus a omega square, at 3t by 4 it is 0, and at again t at it becomes minus a omega square. So if we divide the total time period into equal segments, we obtain the graph. Look here, it is just like the displacement graph, but just it is 180 degree opposite in phase. So it starts from minus a omega square at t equal to 0, becomes 0 at t by 4, then it maxima at is plus a omega square at t by 2, and it continues, and at 5t by 4 then it becomes 0. So this is the graph of acceleration. Thus we can represent the velocity, displacement and acceleration of a body executing simple harmonic motion in graphical form. So we are going to discuss the energy of a body executing simple harmonic motion. So in this connection, first of all we are going to discuss the kinetic energy of a body. expression for the kinetic energy. First of all, we are going to obtain the expression of kinetic energy of a body executing simple harmonic motion. In the last section, we have just obtained the expression of velocity of a body executing simple harmonic motion, which we obtain v is equal to omega into root over of s square minus x square, where omega is the circular frequency and a is the amplitude of vibration. If the body, suppose, starts from equilibrium, these are the maxima points where it is plus a and it is minus a. Now we know that kinetic energy of a body is given by half mv square. So kinetic energy is obtained half m omega square a square minus x square. So this is the expression of kinetic energy of a body executing simple harmonic motion. Now similarly, look here where it is maximum at x equal to 0, that is at the equilibrium position, it is maximum. So it is half m omega square a square at x equal to 0, and it is minimum, it is 0, look here, at x equal to plus minus a. So these are the maximum and minimum of kinetic energy. At the, we obtain that maximum of kinetic energy is at x equal to 0, that is at the equilibrium position, and its minimum occurs at the terminal points. So if we want to plot it graphically, if we want to plot the expression of kinetic energy in a graph, and plotting kinetic energy along the y-axis, and it is the origin, and x along the x-axis we are plotting the displacement. So from here we obtain it is minimum at the two terminal points and maximum at equilibrium position. So if we plot it, we obtained this is minus a, this is plus a. So it is a parabolic nature. This is the expression of kinetic energy if we plot it in a graph. Now we are going to obtain the expression for potential energy. The potential energy of a body executing simple harmonic motion can be defined as the amount of energy stored if we try to move the body in a direction opposite to that of the restoring force. As we know, always the restoring force is acting in opposite direction to that of the displacement. So if we want to move the body from its equilibrium position in a particular direction, we have to perform some work against this restoring force. Now suppose the body is here and we are going to move it along this direction, then the restoring force acts in the opposite direction if we want to displace the body in this direction. So we have to perform some work against this force. As we know, the expression of acceleration is minus omega square x. So the expression for the restoring force acting on the body is given by minus m omega square x. The minus sign indicates that it is in the opposite direction, that of the displacement, that is of the direction of motion of the oscillating particle or the vibrating particle. So if we want to move further against this force or displacement dx, then we have to perform some work, and this work done is stored as potential energy in the body. So the potential expression of the potential energy is given by, it is, suppose we are moving the body against this force from 0 to x, from this point. So it is force into displacement, that is 0 to x m omega square x dx. So we have the expression of potential energy, it is half m omega square x square. If we integrate it, we can obtain half m omega square x square. Now the maximum of potential energy is given by half m omega square a square at x plus minus a, that is at the terminal positions, and the minimum of the potential energy is 0 at x equal to 0, that is at the equilibrium position, just opposite case that of the kinetic energy. Now if we plot it in the graph, if we plot potential energy along this direction and the displacement along the x-axis, so the graph will be, it is also parabolic in nature, and it is minimum at the equilibrium position. So it will be minus a, it is plus a. So this is the graph of a potential energy of a body executing simple harmonic motion. Now the total energy of this body is given by the total energy is nothing but it is the summation of the kinetic energy and the potential energy. So if we write it as kinetic energy plus potential energy, it is given by half, kinetic energy is half m omega square a square minus x square, and the potential energy is given by half m omega square x square. So here we have half m omega square a square. So look here, this is a conserved quantity because all are constant, so it is constant. So the total energy at any point of the motion of a body executing simple harmonic motion is conserved, or it is constant, and we also obtain that total energy is proportional to the square of amplitude. The energy is dependent upon the square of the amplitude. So this is all about the expression of kinetic energy and potential energy of a body executing simple harmonic motion.